Hello, everyone. Welcome to this presentation. My name is Ming Chen from Institute of Electronics and SoC Center, National Yangming Jiaotong University, Taiwan. So I'm going to share with you about my recent um, observation about this entitled Enabling uh, System Design in 3D Integration Technologies and Methodologies. So in this talk, I will talk about some recent research and also the technology for the realization of the system design and especially in the 3D integration and advanced packaging. So let me start with this trending. So in this trending, uh, this is from the Yo research and the article from E Times. So as you know already that the advanced packaging revenue is going up year by year. But why do we really need the advanced packaging? Okay, one of the reasons that you already know is about um, we're reaching the end of the Moore's law. Uh, but um, um, but let's take a look at some of the expenses. So we can reduce to these three reasons. The first is the monolithic chip production cost increase. Okay, so based on the reason of the cost, okay, we will use the packaging, especially the advanced package. And the second reason is about the disaggregating design rewarding. So this means that if we divide into smaller chips, and by using the advanced packaging, and you will get the lower cost to realize your system. But the third one is not really that obvious. Okay, is that based on the high numerical aperture EUV device uh, facilities. Okay, so the reason is that when you go to the high numerical aperture, um, the exposure field size gets cut in half. Okay, so that means that if you want to have a bigger monolithic chip, okay, your cost will be higher. So as you know that this is the basic reason why we were going to the advanced packaging. So here is the outline of this presentation. First, we'll give some technology evolution in the packaging manufacturing. Okay, and then we will update a little bit about the methodologies being used in advanced packaging. Uh, and before we give the final conclusion, we will talk a little bit about the chiplet and its real deal. So is it really a savior for the next generation implementation? And then we'll give our final remarks. So this is from our previous talk. Go back 1 year ago. At that time, we still have the the online presentation. Okay, so let me briefly go through our previous observations. Okay, so at that time, I gave three conceptual observation to try to pave the way for the 3D system prototyping. So the first is to try to have a simple way to disaggregate the design, as I mentioned earlier. And the second is that based on the different application for the 3D system, okay, so we propose the efficient data flow. For example, the DNN AI accelerator in 3D. And then we mentioned about some issues for the constraints when we realize our die-to-die interconnect. Okay, so later I will also detail a little bit more about this part by considering the stagger via and the teardrop. Okay, first, let's see the packaging technology evolution history. So as you know that the conventional packaging usually happens after getting the bare dies from the wafer sawing. So this basically covers uh, the plate through hole, the dip, QFP, and also the we call the high-end um, packaging ball grid array. So going back to 1971, the density is basically around the uh, 19,000 transistors per centimeter square. So the ratio of the IC to the package level integration is around 2,000 to 1. But when we move to the 1990s, the transistor density is going up to the um, on 20s, I'm sorry, the 265,000 transistors per centimeter square, and the ratio is going to around 5,000 to 1. So as you can see that this basically shows the trend of the integration. Okay, so to move to around 2000, the ratio has been up to the zero point 0.5 million to 1. And then at that time, we know that the ball grid array emerged. So, and at the time, we also have the transition from the computing to the mobility. But right now, as you know, that we're going back to the computing. Okay, so we're advancing to the HPC and the AI era. So this shows the advanced packaging that we presented here for the HPC and the AI from the Intel solution. So later we'll talk a little bit more on this. But you can see that they have the EMIB and also the hybrid bonding. They call the EMIB. Okay, and at the same time, actually, both two big companies are developing their advanced technology. Okay, so in TSMC 3D fabric, that include the backend 3D and the front end 3D. Okay, so that include info, CoWoS, and SOIC. So basically, the SOIC solution is for the hybrid bonding. Okay, we will talk a little bit more on the next slide. And also in Samsung, although it's not in they are not as big as the previous two players, they also have their own solutions. So here we show you the report that was just out last month for the it's called the MRH IEP report. This is basically the comprehensive study for the heterogeneous integration that include the previous the HI roadmap. So as you can see from here that with the package dimension going up and also the I/O number and the bandwidth. So there are some current technologies include the 2.5D interposer and the different kinds of the substrates and micro bump and hybrid bonding and also the fan out wafer level package and a panel level package. So here are some snapshots, okay, that include, we just mentioned the hybrid bonding solution in the mainstream, include the Intel EMIB and the TSMC SOIC, and also the fan-out wafer level package. So the interposer is basically costly. It's like a PCB, but has more wires, and we can see that as a secondary substrate. And also, the copper-to-copper direct bonding, it's called the TCB, and versus the hybrid bonding. So the two key differences are, if you want to go below the 40 micrometer, and you probably need a hybrid bonding, okay, but you need to have a higher cost. And also, if you need the wafer to wafer to wafer, or the die to wafer packaging, okay, that's also called the advanced packaging. So recently, there are some companies showing that they have ability to use the standard packaging to achieve the benefits from the advanced packaging, but it's still not that easy. So basically, here we show some issues on the table. We include the reliability issue, and also we should have ability to integrate the right thermal feature to define the physical envelope, and we need to have the bound pitch scaling for the die-to-die, die-to-interposer, and the die-to-substrate interconnections. So in order to have the benefits from the advanced packaging. Uh, So here we introduce the alternative solution is about the programmable package. Okay, the basic idea is to try to use some programmable switch, and then combine with the customized routing layer for those triplets on the top, okay, for the rapid prototyping. Okay, the basic idea is shown here, and also we can have we can take care of the PISI performance. So this shows that with this technology from Taiwan's E3, okay, we can have the very fast prototyping by taking advantage of the benefits from the advanced packaging. So for the methodologies, okay, the main focus are the RDO synthesis, chiplet placement, and the thermal wellness, physical design and simulation. Okay, for this part, I won't go into detail. The reason is that we have other talks, okay, including one keynote speech, and we just show very fast about the part that we're currently working on about the machine learning based routing and SI awareness, and also the programmable package layout design. So we present this paper last year at the SPDAC. The basic idea is to try to use the multi-agent for the concurrent routing on the package. And also for the info, we have some constraints, including the stagger via, so that it can reduce the risk from the stacking via, and also by using the teardrop to try to reduce the crack between the via and the signal. So in our preliminary result, okay, we have some study about by using the ML and the DNN to improve the signal integrity with the single layer and the two-layer shielding, and also we have some method for bounding the routing resource, and we have a new style of the routing. And we're also working on the problem for the pin assignment between the programmable package and the target chiplets. And we need to minimize the number of layers in the customized layer for the cost reduction. So at the end, we'll show you some chiplet issue that we need to um, be aware of. Okay, so basic idea is that if you don't know the boundary conditions for the integration of the chiplets, okay, and you probably need to over design and make it reusable. Okay, so we need to generate the physical, mechanical, and thermal guardrails by developing the modular packaging and the chiplet designs. So it's not that easy to just integrate all of the chiplets. And currently we have some standards, including the D2D protocol, the BOW, UCIe, super chips, and the well-known HBM. So in physical description, we have another talk from TSMC to talk about 3D block. Okay, basically, I think this is a very good idea to try to have the chiplet-based design and also the building block methodology. Okay, so basically the standards for the system design will be good for testing, but the verification will be for the system will be very hard. So disaggregation is also necessary, okay, and also the chiplet discovery. So with the scale down assemble system, we have a fine pitch interconnect will be make the inter dialect communication will be simple. For example, the effort from the super chips. So in final remarks, current HPC AI systems suitable in advanced packaging include the LLM-based and system and also the in-memory computing system. But we need to know that in order to get more benefit, we need to have the system technology co-design STCO for the lower cost and the higher performance. So do we need a predict modeling for a system? We need to constrain the system upfront. Okay, so I proposed to have the advanced packaging design cost feasibility study. Okay, this concludes this presentation. Thank you.